Hello, and thank you for joining me. Today we're picking up where we left off last time in the LSTM stock prediction. We're going to take it a little bit further, go further steps, and really spend some time on the time series analysis this time and try to really extract as much as we can from the time series data sets. Okay, so what we're going to do is we're going to start off by importing our drive. So from Google dot drive, or sorry, do google.colab, import drive, and then drive.mount. Okay, so this is connecting. And then what you need to do as well, we're going to use the R squared. And with that, we need to use a TensorFlow add-on to allow us to access that. Google Colab doesn't have this automatically installed, so we need to install it every time. If we're using Colab, once you've installed this once on your computer, then that should be fine. So here we'll do TensorFlow add-ons. Okay. So pip install TensorFlow add-ons. There we go. There's some really cool stuff here. I haven't really explored the whole extent of this library, but I think it's pretty cool. Here we're importing our libraries. What we're going to do is TensorFlow add-ons as TF. And then our other standard libraries, TensorFlow, NumPy, Pandas, Seaborn, PyPlot, and Standard Scale. Okay. What we'll do is from statsmodel.tsa.seasonal, we'll import seasonal decompose. And from statsmodel.api, we're going to import SM. Okay, I'll need both of those today for seasonal decomposition. This is probably the one reason that I use stats model. Why would you go back to modern stats when you have machine learning? But the one reason I use it is for the seasonal decomposition. One of the main reasons that I use it for seasonal decomposition. So we'll import our drive. This is in my reservoir, so you'll be able to run this cell and we'll import it directly from my GitHub reservoir. We're looking at the data, inspecting our open, high, low, and close values, volumes, shape, 4,000 rows, 7 columns. Okay, so we're gonna have our palettes right here, and we'll use that as we're plotting today. So we'll go a for loop to plot all of our distributions. So df.columns, and here we're gonna do is we're gonna go data equals df, x equals feet, and color equals palette, and we're going to index from position 1. And we'll go plt.show and plot that out. And I got to run the syllable first. Big surprise. That never happens in my videos. Okay. So here we go. We have the distribution. As we've seen before, we have a lot of exponential distributions, which are really common in financial data sets. So to be nice, we're not going to do any of the financial indicator development, but they're all ready to go. So we're going to do MACD, RSI, fast K. So this is from the fast stochastic indicator. The K is the black line, is the one that moves faster, and then the D is the one that moves slower. And so this is one of my favorite indicators. And so I'm using it today. So let me make sure I'm running these cells. We're going to do MACD, and then RSI, and then fast K, the denominator of the fast stochastic percentage change feature, and then we might as well visualize all of them. So what we're going to do here is visualize the indicator. So here we're going to do select the features we want to plot, and those are the indicators we want to. We're going to go pl plot, and then we're going to go kind equals line, color equals palette, subplots equals 5, and layout equals 5 by 10. And the last one is big size. Okay. So run that, and we get our nice little plots. And the big important thing here is that we can see that these are stationary. There's not a big scale up or down to them. So they are stationary. We do see there's outliers in some of these, but again, they're stationary. That would be the important thing. Really important to remember with financial data is we need stationary data, and that was done up above. I did first differencing to get the values. So here we're going to drop the outliers, or sorry, the null values just from the indicator development. We get a few of them. Okay, so now going into the seasonal decomposition. I remember the first time I saw this, I was just amazed how cool this is. Okay, so here we're going to create a seasonal decomposition object, which has the trend, the seasonal, and the residual time series file. So it breaks it into 3 different parts. So here we're going to call what we imported the seasonal decompose, and we're going to give it the df, and we're selecting the feature from this. Then we're going to go model equals additive and freak for frequency. And there we go. So we're going to plot, and this is going to give us an additive seasonal decomposition, and the frequency is going to be what we get. We're going to set the standard as 5, just because my personal theory is that the stock market follows at least this pattern. It might be a 15-day, it might be a 30-day, and you'll be able to experiment with that, and maybe you can make your model perform better than I can. Okay. So here what we're going to do is we're going to do plot.subplots. And we're just going to do a 1 by 1 of this, and I do this to create the axis object. Okay, so we do the subplots. We then do sm.graphics.tsa.plots.acf. Okay, and here we're going to do our C's decomp that we did, the object that we have up above here. So these are the same names. We're then going to do seasonal, because we want the seasonal version of this. It could be trend or residual, as you see here. And then we want to get the values, turn it into a NumPy array, and we'll squeeze those. And then we're going to add the lag is equal to the LGS above, so lags. We're then going to put our feature into the title name as well. So feature into the title name, and then we'll get a nice plot. So that's our function, our seasonal decomp plot. We go down to the MACD down below. We're going to go seasonal decomponents. Components underscore plot. Okay, or component, that's what I'll do, components. So let's just copy and paste that and put that right here. The name of my function, I'm going to bring it down here. We're then going to go frequency, FRQ is equal to 5, so 5-day seasonal pattern. And then we're going to do lags equals 30. So these are default, so you can play around with this, and I would say the most likely is a 15-30-day pattern in the stock market, and there's probably yearly, quarterly, and so on. So it's good to play with. I think a 5 is the smallest number there is, and there's a weekly pattern to the stock market. I think that's fairly straightforward. So here what we can see is we have the auto correlation. So this is saying the 1 day into the past has with itself a close to -6 correlation with -0.6 correlation with itself. So this means that, it's high negative correlation, strong one here as well. We can see this one as well, and we can see, so we have a pattern of 1, 4, 5, then it repeats 6, 9, 10, 11, 14, 15, and you can find your own patterns. This is what we'll use in the loop to generate our time series features. And so I'm just making a list for each one of these, and just again going through looking for a pattern of which days are the most correlated with itself, and then again hopefully this is correlated with the price, as these are indicators of the price. So, and again going through and looking for the different patterns, we can see sometimes they repeat the 1, 4, 5, or in this one we can see it's a little bit different here. It's 2, 3, and 5, 2, 3, and 5, 2, 3, and 5. So it goes to the same. And so this way we're getting kind of like a patchwork. We're not getting the full time series past, but we're getting a patchwork of the days that are most correlated with each indicator, which gives us the full amount, but we extract which days are most correlated with each indicator. So keep going through this, doing again the same thing, extracting the pattern and putting in, we're going to do the last 20 days. You can go up to 30 days, 60 days. I found up to 30 days is valuable. You could probably go even further than that and extract some value from that. So just doing again that for every single one. Here what we're going to do in the next one, we're going to create a loop for these, and we're going to plot through these, and we're going to shift them all by the same value. So here what we're going to do is we're going to need the names. We're giving our list of tuples. So here we're going to do macd, and then we're going to do macd days, which is the list that I created up above, and then RSI days, and we're going to use the name for the title of our plot and for our features to extract our column, and then this is the list of the days that we're going to do time series extraction from. So we're going to go 4 days in feet days. We'll then go day for day for D in days 1. So for D in this day. So we're going to take this out, and then what we're going to do is we're going to go days 0. We're going to get from this one, so we're going to get macd, and then inside this we're going to put D. We're going to put, and then we're going 1 day into the past. Here we're going to go days 0. We're selecting 0 from there, and then we're going to shift it by our day. So let's run these 2 cells. Okay, so let's run these 2 cells, and here we'll do our loop right here. Feet days. Oh, feet days. Got to spell things correctly, and there we go. So if we inspect our head, we'll see we get a very large data set now with the time, and these are going to be null because we're moving things from the past and the future, and there's just not going to be values. If we inspect just the macd, you can see here that they do have followed the pattern of 1 day behind, 4 day, 5 day behind, if you wanted to inspect that in detail. Okay, so just looking at how many null values, we're going to have some null values from the time series creation. We're going to drop those here. df.na. Let's get into the modeling section. I like to look at the columns, and what we'll do is I'll copy and paste this, put those in a list of the features, and then I'm easily able to select in and out which ones I want to do. So I'm doing that for a list of features and a list of the target. I'm picturing or predicting the nominator of the fast gate. You can do macd, the price, whatever you wanted, because we're using the past. You just have to make sure that we have the data available. So you can't use today of another indicator to predict today of the same, another version of the price. That wouldn't work. We have to use yesterday's price, which we're using macd 1 day into the past. And so again, you have lots of choices of what you would like to predict, and it really does make a difference on how well it does. So in split equals 4. We have a big data set today, which is why I chose this one. Really good for neural networks to have lots of data. So here we're going to make sure to run that feature cell, and here we're going to make 400, and we're going to select the first 400 rows. So in split first 4,000 rows, sorry. And then we're going to select, because we're doing a time series split, we're just going to split it like this in terms of sequential. Okay. And you just need to, again, always make sure you spell things correctly. All right, so you're split there. Okay, and we can see no null values. We're then going to put our features and then our target into the df square brackets, select out for x train and y train, then for x test or df test, we're going to go features and select up the features and the target for the test. Okay, so run those 2 cells, and we have our list right here. Okay, so let's standardize your data set, always very important. So standard scalar, and we'll fit this as we're importing it. So we'll fit it to the X train data. Oops. And I have to finish this. So we'll go standard scalar dot transform, and then transform the test data. And we're calling that on the object that we fit in the first line. And then here what we're going to do is we're going to grab the dimension. So we're going to go shape 1. It's the second position of the dot shape, which is the number of columns. Okay. Getting into the architecture, do a little bit more architecture today to get some practice. So here what we're going to do is the ALU. I like the ALU is my favorite. I found this, we did a lot of experimenting on this data set to try and bring you guys a good architecture, and I found ALU, I always really find it works really quite well. So the epochs, the learning rates, the loss is going to be MAE, mean squared error as well. Here what we're going to do is we're going to import SGD as the optimizer, stochastic gradient descent. And here we're going to assign the learning rate from just a couple lines up above. Rate. So learning rate. Send that there. Okay. And so here, what we're going to do is we're going to go tf.keras, defining our sequential model, tf.keras.layers.lstm. Okay, and we're going to give it the recurrent activation. Okay, and our input shape is the dimension, the number of columns, but we also have a depth. The recurrent needs a depth, so the kind of X value, and that's what this one is. It's saying kind of like there's one spreadsheet. If you had green, blue, red, it makes more sense. If you have 3 channels, so your dimension would be 3. You have a depth of 3. Here in the spreadsheet, we only have a depth of 1, but we still need to define it. Okay, so our second layer is going to be a dropout layer. It's super important to make sure our model doesn't settle on one path through the network. So here we'll do dense, dropout, and then dense. Doing this in the deep belief style of a network, so kind of an ebb and flow style of network. All right, it works very well. We'll do another dropout layer after a little bit of ebbing and flowing, and then 2 more dense layers right here. Okay, so we'll define that. And here we're going to do, when we compile the model down below, we'll model.compile loss equals the ls from up above. The optimizer equals the opt optimizer from up above. And metrics, here we're going to do is we're going to do r squared. This is going to get us the r squared from the TensorFlow add-on library. We're going to get our r squared right there. So we get that, and then just need to make sure there's not that one extra equal sign right there. So run those 2. And our model is compiling. So there we go. And we got a little warning, but that's not a big deal. So we do history here. We're going to do model dot fit our x train, y train, validation underscore split is just 20%. Our epochs, our EPS, and because to make it a little bit faster, we're going to do 256 rows. So batch size is 256. Okay. So let's run this, and we're going to go for 800 epochs. Let's go for 500 so that we can get this done in a reasonable amount of time. Okay. So we'll go for 500 epochs to get this done. I've gone up to 2000 and I found that it kept getting better. So I would recommend going for more on your own and try and see if you can improve upon my R squared. So let's fit this model. And you can see here we start off with a really terrible R squared. I find that very interesting, but we'll see that it starts to move in the positive. We're not going to get a very high R squared because we're just using itself. We're just using the patchwork of the past time series values. So there's a limit to how good we're going to do, but we're trying to extract what value we can from its historical pricing, and then adding this to economic data one day will be, I think, really powerful. So we'll see that when we get to it. Okay, so let's wait here for our model to train. Okay, and just finishing up here, we're getting our square root of kind of 7, 8 sort of thing, 6, 5, 7, 8. I've gotten this up to 0.0 0.2, an R squared of 0.2, which is pretty good. This is a very short run. It usually takes about 2,000 runs, so definitely play around with it, play around with the architecture. Let me know in the comments if you get above a 0.2, and what we'll do is I'll add your kind of concepts of architecture to my next, and we'll kind of work on this as like a team and make the project kind of develop together. And use, if you find out better architecture, I like to use that because as we add more things in, I'll just continue to build on your good ideas and mix those with hopefully some of my good ideas. Okay, so we've trained our model now. What we're going to do is we're going to plot the history. So the easiest way to do this is to put it into a data frame. So pd.dataframe, we're going to go history.history. And so this gets all of our functions. And so it gets the val and the loss of the val and the train of the loss, and then the other metrics that we're calling it. So here we're going to go color equals palette, layout equals 1/4, and big size equals 12/14. Okay. And sorry, that was not layout, that was subplots. So subplots 1/4. And you can see here we get our distribution. It does start to, it's kind of like it falls into an extra hole down here. So there's lots to try. Try and predict different indicators. See if an indicator or even the price matters. Expand the neurons, take away, play around with the dropout layers, play around with the number of dense layers. Lots to do. Even different optimizers would be good to play around. So it's really set up to experiment with. Try different activation functions and see if you can beat my 0.05 R squared, but really my best has been a 0.2. So see if you can grade a 0.2 and let me know in the comments if you can. And here we're going to do the R squared, the model.evaluate of the train and the test. Okay, so really, really good job. We're getting an R squared of 0.12, 0.12, so it's pretty good. Again, for a very short training time. Still took a little while, but very short in consideration. So thank you very much for joining me. I look forward to hearing from you kicking my butt in the R squared, and I will see you for the next step in this project. Bye.